Hi everyone, my name is Sam, and I'm excited to present our paper ShapeGrasp, Zero-Shot Task-Oriented Grasping with Large Language Models through Geometric Decomposition. Let's start by taking a look at the challenges of zero-shot task-oriented grasping. Real-world robots struggle in unstructured and dynamic environments, such as in the household. There may be many unfamiliar objects, diverse instances, or tasks not seen in training. Toward enabling useful robotics, the goal of this project is to understand which part of an object to interact with, and not just the object itself, for diverse tasks. Let's think about how humans might be able to do this. Given an arbitrary object, humans generally know how to grasp it. For example, chances are you haven't seen or interacted with this exact dinosaur mug instance before. But as humans, by knowing it's a mug, we can reason over this novel instance and confidently manipulate it in various ways. One line of reasoning we may use for this task is to break the object into parts and interpret and understand them as shapes or other high-level symbolic representations with associated qualities for part-level reasoning. We would like to use a similar idea or intuition for robot grasping. Toward that, we propose to use the common sense reasoning capabilities of LLMs to extract relevant and actionable semantic information and knowledge. We query this knowledge in a constrained manner by providing an initial shape-based symbolic graph representation of an object's parts, similar to what we showed in the previous slide. This graph handles low-level geometric and visual properties, such as the size and location of each part. We reserve the LLM to do what classical vision techniques cannot, which is open-end semantic and affordance reasoning over these parts in a grounded manner. The LLM generates semantic hypotheses for each object part node. In essence, what this gives us is an augmentation that takes us from the initial geometric graph to a full semantic graph. By understanding an object's parts and unlocking these semantic properties, we can interact with objects in different ways depending on the task, demonstrating the sometimes subtle task-oriented reasoning that humans easily perform, but robots often struggle with. Here we have the same mug, and our pipeline understands the semantic parts and their significance for these two tasks. In the case of the first task, which is to pick up the mug, the robot picks up the mug by the handle, as you may expect. For the second task, which is to hand over the mug to someone, the robot grabs the mug by the body, as you may naturally desire in such an interaction. The unlocked semantics and knowledge through engaging the LLM with this symbolic structure graph allows for this part-level affordance reasoning. Now let's dive into the details of the pipeline. The first stage is constructing this geometric and visual shape-based graph. With the object in the workspace, we take the sensor inputs and perform a convex decomposition using an off-the-shelf third-party model. Notably, convex decompositions are fast and give us a geometric breakdown of the object. However, there are challenges and limitations in using convex decompositions we need to address. We may have bad depth or highly concave objects, such as a mug, that do not decompose well in 3D. So we also introduce a 2D decomposition option that doesn't rely on depth inputs. We take the object contour or mask and decompose that flat 2D surface. The selection between the two procedures is done via a heuristic that considers the depth confidence and total number of decomposed parts. Back to our mug example, the heuristic would look at the 3D result and switch to the 2D decomposition. There's one more component to the heuristic of decomposition in regards to the convex decomposition error threshold. This threshold determines how exactly the decomposition reflects the original object and controls the number of decomposed parts. Looking now at the number of decomposed parts, which is one single part, the pipeline would adjust this threshold down to give us a more accurate decomposition, in this case of two parts, the body and the handle. Now let's briefly skip ahead and look at some ablation results that speak to the usefulness of this dynamic decomposition procedure. You'll notice that both the 2D and 3D pipeline in isolation do not perform as well as the heuristic, which can leverage the benefits of both. From here, the rest of the pipeline and graph construction stays the same. Now we take that heuristically provided convex decomposition and we project the convex parts into the RGB image to get these 2D convex holes. Each convex hole is approximated with a basic geometric shape, such as a triangle or a square. And Each decomposed part is then represented in this initial graph with visual attributes, such as the size and color and their relationships. To give a full example of what this initial graph looks like, in the case of these sunglasses, we have two rectangles for the arms and two ellipses for the lenses, with edges that connect the parts that are connected, and attributes per node contain the shape, center, the area, the aspect ratio, the angle, and the color. Now we start the LLM interaction stage. So the graph is represented in language and given to the LLM with a task for open-end semantic reasoning. This is a key point in our contribution. We use the LLM to assign semantic meaning and relevant attributes to each node in our symbolic graph, and only the nodes in the graph using these visual attributes that we provide. So we control the relevant information as well as the granularity of the part level reasoning. For example, here we wouldn't care about the nose pads of the sunglasses. So using its common sense reasoning capabilities, the LLM can infer that the two rectangles are the arms and two ellipses are the lenses, and thus unlocks numerous associated properties such as part functions and what is stable or fragile, all of which are tied back to the graph nodes and the geometric properties that we can use to map these semantics back to the real-world object. Now, with the full symbolic and semantic context in our augmented graph, we follow with the task reasoning step. This is the last step in the reasoning pipeline, and it is a crucial and separate step from the previous steps. The part semantic reasoning may not depend on the task, but how we interact with these parts does. So with this full semantic context, the LLM can select the arm as the part to interact with for the task of picking up the sunglasses in a straightforward and common sense manner. Let's take a look at the exact prompt that we provide to the LLM. So we start with the name of the object and some general task information, and then initial graph represented as a set of as a list of nodes and edges. In the first step, we ask the LLM to reason in an open-end manner about what semantic part each node may represent. The LLM tells us its reasoning and that it thinks the rectangles are the arms and the ellipses are the lenses. This is exactly the information that we want, but we can't use this in our code directly. So we follow this up with a structured prompt that just asks the LLM to kind of reiterate its previous free-form response with all that context in this structured JSON output. So the sunglasses and the the lenses and the arms were assigned to those parts. This is the semantic part identification stage. Similarly, in the next stage, we ask the LLM in an open-end manner to think about what the correct part is for the group to interact with. The LLM tells us its reasoning about why it thinks the arms are best. These are stable and it's safe, effective, and durable, whereas the limbs are more critical to the function and easy to damage. We again ask it to assign in a structured JSON format. In this case, it's a likelihood score for what the part is, the correct part is. So the rectangles get high score and the ellipses get low score. This is the task reasoning stage. And with these two stages, we complete the task-oriented selection based on the first semantic part identification. So let's go over the pipeline again and see it in action, this time with a hammer. So we start with this shape decomposition for the initial symbolic graph construction. We augment the graph with fine-grained semantics and affordances from the LLM. In this case, the rectangle is assigned hammer and all those attributes. The ellipse is assigned the head. The LLM then uses the full symbolic graph to reason about the task utility of each node. For the task pick of the hammer, the handle is given a high score, and we use a simple end effector controller to send the robot there to execute a grasp. And for the task hand over the hammer to a human, it gives the head a high score to leave the handle available. And we can execute a different grasp with the same input graph in the same semantic context, illustrating how the augmented semantic graph is useful for this nuanced task-based reasoning. We evaluate our pipeline on the problem of task-oriented grasping using a data set of 38 common household objects from 12 categories, these are some of them, across 49 tasks. Categories include groups such as bottles and tools, and many objects are associated with more than one task to reflect the diverse ways we can interact with objects. We use this diversity to demonstrate the open world and zero-shot reasoning capabilities of our pipeline. Now let's look at some results. We'll first go over the metrics. We start with the part identification metric, which is the accuracy of identifying each part in our decomposition across all parts that gets decomposed and across only the target parts. What this means is that for every object task pair, there is a part that is correct for interaction. Notably, if the decomposition fails for any reason and the correct part is not actually segmented, this would automatically also count as a failure here, because we can't identify the correct part. Part selection is the percent of time that we select this correct part. And lift success is the percentage of ShapeGrasps executed at the target parts. And there's sort of like a compounding effect to these metrics. If the part selection is wrong, the lift success would also be counted as wrong. Part ID is wrong, and the part selection would also be wrong. We also look at time, which is just the inference time in seconds, because we care about having an efficient pipeline that we can reasonably run on a robot. So our method outperforms other state-of-the-art zero-shot task linear grasping methods like GraspGPT. GraspGPT uses LLM to relate novel objects and tasks to occurrences seen in training to execute a similar grasp. This large gap may be in part due to the noisy sensor inputs, which we robustly handle with our 2D, 3D heuristic. And also everything is unseen, so GraspGPT has to relate every object task to something it was previously trained on. We also evaluate against GPT-4 vision. We take our segmentation and we color and index them. And we use the same task and prompt, but with this grounded vision input instead of structured language input to select a part. We see about a 10% improvement here as well. And this may be likely due to the fact that this is sort of less constrained. The VLM needs to figure out all the visual and geometric attributes that we robustly extract, and it has to stay grounded to these parts while seeing the entire object and image. Our pipeline is also modular, so we can switch out the reasoning backend to use a small open source local language model instead of like a huge state-of-the-art language model like ChatGPT. And here we see reasonable performance as well. There is one more cool aspect of our pipeline that I would like to point out. If you give the pipeline a standard task, such as grab the wine bottle, it will pick it up by the part that you expect, the larger, more stable body. However, maybe you have a really small grouper. And if you provide that constraint in the prompt, and you also provide this additional attribute of width in each node in your graph, which can be easily extracted and just added to the graph, the LLM can change its inference. It understands that physical constraint on the robot, and it picks it up by the secondary part that still works. So we have flexibility in the prompt, the graph, and the LLM open entry for reasoning, so you can tailor the properties, attributes, constraints across not only the object, but also the robot, and potentially other components as well. So in summary, we present ShapeGrasp, a novel zero-shot task-oriented grasping approach that represents an object using a structured symbolic graph, and then engages an LLM for guided hypothesis generation for fine-grained, part, semantic, and task-oriented affordances reasoning. Thank you.